thanks Mario for like agreeing to talk. And Mario, I guess he did his PhD with Anton Zellinger, and I mean, and currently he is at University of Toronto with Alan Oskorobuzik, and I also see Vector Institute there. Like, so probably he's working there also, and he's one of the, I would say, like finest people like who are working on like how to use AI to like basically replace scientists. I mean something like that. I mean so
Nah.
so how to get ideas and
It's
all
true. It's true.
that.
No, no, no.
so
I
so
don't
yeah,
agree.
let's see to what extent like Mario can get successful, and it's incredibly exciting. Like I mean, and so I would want Mario to like present his ideas and yeah, like Mario, the stage is yours. Yeah.
Yeah, thank you very much. Thanks for inviting me. I would not agree at all that the plan is to replace scientists, but to accelerate science. And this, I think, is possible. Just helping scientists with different tasks. And I think also that we can help with AI. We can help on a creative task. And this is one way how I hope this could be done in the future. So yeah, thanks for inviting. Um, I would, I want to explain you here how to create a semantic network in quantum physics and how to use it to predict and maybe suggest new interesting research ideas. So prediction, okay, we can do it. The suggestion is ongoing research. And yeah, so this project was motivated by the question of how we can use computer programs actually to inspire surprising and interesting ideas. So in order to answer this question, we need to know, of course, what does it mean that something is surprising or interesting? And this is obviously very subjective and depends on one's previous knowledge. So now the natural question is, how can we get this previous knowledge into a computer in order to answer this first question and to come to this goal? So I was puzzled with this question for quite some time until I found this wonderful, inspiring article. This is an article of a collaboration between computational sociologists and biochemists. And the article is building a semantic network in biochemistry. So they see research programs as links between scientific concepts in an evolving knowledge network. So in their network, the vertices are names of biomolecules. And the edges between two vertices are drawn when two biomolecules are studied together in a scientific article, or to be more precise, when they are mentioned together in the title or the abstract of an article. And they then use millions of papers and patents that are published over the last 30 years to build up an evolving semantic network. And they show with some sophisticated statistical methods that they can actually propose more efficient or potentially more efficient research strategies for the collective scientific community. So I was super impressed by this article and wanted to do the same thing for quantum physics. So the first question here is, how can we get this concept list? How can we get these vertices that they use as biomolecules? How can we have something like this in quantum physics? So how to get a concept list in quantum physics? Unfortunately, such a list doesn't exist, so we need to create it ourselves. So what I've done is I've used knowledge from Wikipedia, from quantum physics books, and from 100,000 of papers. To be precise, I've used every title of an article that is in Wikipedia's category of quantum physics. These are a few thousand. Second, I used roughly 20 or 30 books in quantum physics and photonics and atom physics and so on, and went to the indices and copied every word that is written in the index and combined it with the list from Wikipedia. So, and that created a list of roughly 5,000 concepts. And those are high quality concepts. They are human compiled, so by human experts compiled, but they are not very timely. So the recent trends are missing, are very often missing in Wikipedia or physics books. So I also downloaded all articles that have ever been published in the quantum physics category on archive. So these are roughly 100,000 papers. And on these 100,000 papers, I took all of the abstracts and the titles and applied some natural language processing tools. And those natural language processing tools, so specifically one that I used was called Rake, they can extract key concepts in a written text. So together now with this human compiled list, I have an automated created list, and I combine those two lists. And together these are roughly 6,000 or more than 6,000 concepts in quantum physics. And this is our final list from which I create the semantic network. So now I have these vertices that the biochemists have. I have now the vertices. And to form the edges, I use a similar strategy. I form two edges when two concepts are studied together in the scientific literature. Or better, I combine the two vertices, so I draw an edge between the two vertices if they are studied together in a scientific article. And for this, I use the 100,000 articles from arXiv, plus every paper that has ever been published by APS in the last 100 years. So these are additional roughly 6,500, 650,000 papers. So in total, I have roughly 750,000 papers that go back to January 1919. And from this list, together with the concept list, I create an evolving network. So for every paper where two concepts are mentioned together, I share they share a link. So I can give you a simple example. So here there's a paper from 1995, and it uses the word interaction-free measurement, and it uses the word, for instance, single photons. So now we go here to this mini semantic network, and we see the concept single photon here and interaction-free measurement here. And here I draw a link between those two concepts, and this link is drawn for the year 1995. And now another example is here, 25 years later. Interaction-free measurement is for the first time connected with Leggett-Gach inequality. So again, interaction-free measurement is here, Leggett-Gach inequality here. So this link in the whole network is drawn for the first time in 2015. And this is how the semantic network evolves. So now, this is a snapshot of the whole semantic network. These are the 6,000 vertices with the edges that are built up from 750,000 papers from the last 100 years in quantum physics. We can now perform a few interesting sanity checks. For instance,
Mario,
yes?
can I ask a question?
Sure, sure.
So like, I mean, do you also add nodes like as it evolves, or like you only keep on adding edges?
So, so the nodes are created in the very beginning. So this is this concept network. So this is this concept list, and they are fixed in the beginning. In the beginning of the evolution, most of the nodes are not connected to anything in the network. So they are just loosely flying concepts that don't have any meaning yet. But after the time, they are connected to this whole network.
But sometimes, like, like, I mean, as science, for example, evolves, like new
Yeah,
concepts like
yeah,
come, right?
yes,
So like,
absolutely.
sometimes
And
like,
this is a very important and very difficult question.
yeah,
There's actually quite a lot of study in network theory or also by computational sociologists how to find new concepts and how to predict new concepts. So how can you add new concepts uh, yeah, in an automated way here. But here I just took all the information that I had at the very end, created all vertices that are possible, and they are forming the basis of the network. So we can also zoom in now to this network and see, for instance, here this is one cluster where we have together faster than light communication, Bell's theorem, quantum non-locality, and so on. So we see that semantically close words, concepts that are closely connected are also closely connected in the semantic network. We can take another example. Here in the bottom, we see decoy state and BB84 and quantum key distribution. They are all part of the larger idea of quantum communication. And they are also clustered together in the semantic network. So we see in some sense, the network stored some meaningful relations between those phrases. So what we can also do is look at emerging concepts. So these are concepts
Sorry,
that...
may I ask you something? Sorry.
Sure.
In the previous transparency. So if a relation between two concepts appears in very many articles rather than in a few, the intensity of these lines should be proportional to that, no?
Yes.
But these lines are only established if a single paper does the connection, or?
So the line is established as soon as one article combines the two, and this the weight of that edge is increased the more papers use these two phrases together. So yeah, it's a weighted network.
And the clusters in general, to clusterize, you need the concept of a distance. So how do you find the distance here?
So what I do here is I use some simple network plotting tools that can think about such a network as a mechanical thing where there are springs between every vertex, and the strength of the spring corresponds to the weight of that edge. So the stronger, the more papers combine two concepts, the stronger the spring, and and then the idea of plotting such networks that gives you some meaningful semantic connections. The concept is to just try to relax this whole construction. Was this roughly clear?
Yeah, if I understand well, the number of appearances brings the concept of a distance. Okay, I the tools I understand. I mean, there are many tools to relax this, but in the very deep concept of clustering strategies, you need a distance metric. Okay.
Yes.
So you understand the metric is provided by the number of papers that that put together the concepts.
I think for plotting it here, you can see it that the strength of this virtual spring corresponds to something that can be used for yeah, that gives you this clustering in some way. Because clusters that are closely together have many edges between them. That means, virtually speaking, they have many springs, so they are held together very tightly. And by that you find this automatic clustering.
Yeah. Well, just to finish, I don't want to interrupt you more, but you know that
Sure,
clustering belongs to a difficult category.
Yes.
It is very often ambiguous. Just for curiosity, you know, you may know that the best algorithm is now from a person from Toronto in 2007, all the message passing algorithm. So, well, you know, clustering is always very subtle. That's
Yes.
why I was asking. But go
Yes.
ahead,
Yes.
please go.
To be clear, I will not use any clustering later. This is just for visualization to indicate that this network has some meaning, or that some semantic meaning is encoded here. Because, for instance, if we would see that there are very close vertices with completely different meaning, that would be an indication that something went terribly wrong. But this is not the case here. So we can say, okay, it's fine, we can analyze further. Kind of a sanity check, a simple one. Definitely not at the level of clustering. Okay. Okay, so let me show you a different way how to analyze whether the network stores some meaningful information. We can analyze emerging concepts. So those are concepts that haven't been used before, but as soon as they are used, many papers start to use them. And we can find here many interesting cases. For instance, in the late 2000s, we see topological insulator, one of the fastest growing concepts that has not been used before. And we know in 2016, the Nobel Prize was awarded for a related topic. We can also see, for instance, here, the fastest growing concept in the whole history of quantum physics is the concept of qubit in the late 90s. And this is very interesting because qubit kind of combines quantum physics and information theory. So in some sense, one could say that the emergence of qubit and the growth of qubit kind of indicate the birth of the field of quantum information science or quantum information theory. There are many other ways how you can see it, but this could be one way to see it. And very interesting, the very last the very last concept that emerged very fast is quantum machine learning, which is perfectly fitting for this seminar. So from 2012 to 2017 or 2013 to 2018, the fastest growing concept was quantum machine learning in all over quantum physics. Yeah.
Mario, but for the lines, let's say, for example, squeeze state, what do you mean that it stops around 1990?
Yeah, so I only plot always the first 5 years. Because
I see.
Here, I mean by emerging specifically phrases that are not used at the year X, that started to be used at X plus 1, and which one is the largest at X plus 5. So after 5 years when it has been introduced the first time.
Right.
Okay, so we can look at a similar thing for emerging connections. So which edges have been drawn the first time, but then investigated very frequently. So one thing in the mid 2000s is microwave and qubit. So of course people started to investigate microwave qubits and microwave quantum computers. Also closely after that, cluster states, which is a theoretical concept connected with graph states and so on, and photons, which makes perfect sense because graph state was a very good way to perform photon-photon interaction in an indirect way, in some sense. Okay, so now that we have the evolution of the last 100 years, the question is, can we say something about the future? So we see how this semantic network evolved. Can we say something about the future? And a precise way to formulate this question is which unconnected pair of concepts, so which two concepts that have never been investigated in a scientific paper, will be connected in the next 5 years. So, and for that, neural network seems to be a very good choice, but unfortunately, the semantic network is way too large and complex as a direct input. You can think about it as a very complex, discrete data set that you can represent with a 6,000 times 6,000 dimensional matrix. So this is way too large as an input, at least at the time when I was doing it. There are probably people who can do this, and I'm hoping to do this at some point. But to go around this problem, instead of putting the whole semantic network into the neural network for predicting, I choose pairs of concepts that have never been connected before and calculate a number of network properties of these two concepts. The number is, I calculate roughly 20 network properties, and those network properties could be, for instance, what is the number of papers that use concept A? What is the number of papers that use concept B? What is the what are the shared neighbors of concept A and concept B? What is the network distance from A to B? What is the number of path of length 1, 2, 3, 4, and so on over the last few years that connect A and B? So those properties I calculate for every unconnected pair, and these are then the input into my semantic network, into my neuronal network. So the training looks like this. I take the semantic network from 2012. I calculate for each unconnected pair, I calculate 20 network properties, and these 20 network properties are now the input into my neural network. And the neural network has to predict whether this unconnected pair will be connected 5 years later. And I have the I have the semantic network from 2017. That means I can give the perfect supervision signal. And yeah, and after this training, I have the neural network that can perform the link prediction task. So which can predict which two concepts will be connected over the next 5 years. And now at this point, I can apply different data to the neural network that it has not seen before. For instance, at this point, I can input the semantic network of 2017 and predict what happens in 2022. So now at this point, after the training, I can try to predict into the future. Question is, what is the quality of this prediction? And in order to quantify this, I have to introduce one concept here that is called receiver operating characteristic curve. Who has heard of that before? Anybody? No? Okay, good. I also didn't hear before I did this. So, okay. So the idea is that I take every unconnected concept from my semantic network, and these are roughly 30 million concept pairs. And all of those 30 million concept pairs are put into the neural network, and the neural network predicts, gives a rate whether it will be connected in the next few years or not. So it will give some probability. But now I sort this concept by very highly predicted to very unlikely to be connected. And then I check whether it actually has been connected. So I take the highest predicted pair and check, has it been connected? If it has been connected, I take an arrow here and go into the upwards direction. If it has not been connected, I go one step in the right direction. So let's say our highest predicted concept pair actually will be connected 5 years later. So we take a step up. Now let's take the second highest predicted pair. Let's check. And it also has been connected, so we go a step up. Let's take the next one, the third one. Let's say it's not connected. We take a step to the right. And we do this for all of the 30 million unconnected pairs. And we build up a curve with that. And if you think about it, if the prediction would be totally random, it would be totally randomly distributed whether you go up or right. So for random predictions, you get the diagonal. And the better your predictions, the higher your ROC curve goes. So then to quantify our prediction quality, I also performed this ROC curve, and we see that all of those curves are very high up and significantly different from random. And one can actually also think about operational meaning of this curve, namely by calculating the area under the curve. So the area under the curve for this random prediction, which is the diagonal, is 0.5, okay? And the area under the curve for our prediction network is roughly 0.85. And this can be interpreted as the percentage that a random true element, which means a random concept pair that will be connected in 5 years, that one is higher ranked than a random false one. So than a concept pair that will not be predicted, that will not be connected. So in our case, our network can with 85% predict a random true element higher than a random false element. And yeah, usually everything beyond 80% is considered a reasonable prediction. Yeah, this is 85. Okay, now we have this semantic network and the neural network that can predict into the future. But now we would like to go back to this question from the beginning, to go towards suggesting some topics. Yeah, so this suggestion was actually the goal from the beginning, and we would like to go now towards those goals. So I would like to have a tool that can give me personalized suggestions. And in order to do this, I give you now an example. Okay, no, I'll show you first something else, why this is important. This is not only important because it would be quite interesting, but also because the number of papers in quantum physics just grows and grows and grows. So here on the left, I show you the number of papers that are on arXiv, that are posted on arXiv every month in the category quantum physics. And you see it's kind of a linear increase. And recently there were more than 800 papers every month posted on arXiv, which is crazy. A single human scientist can not really grasp all of this information anymore. And the situation is even much more extreme in the field of machine learning and AI. So the number of papers that are posted every month grows exponentially with a doubling rate of 23 months. So this is crazy. How can human scientists keep up with this? It's surely impossible. So we need something that that deals with this problem. And now let's think about such a tool that can suggest new ideas. So the thing that it would solve is, in this case, it would solve that you can get ideas that are far away from your own research interest, or far away from your own experience that you have from the papers that you read, but that hopefully still makes sense in some way. So that would be the goal, to suggest some ideas that are in some way connected to your research, but actually also outside of your field, but that would make sense. But that would be a goal. Now let's see how we could maybe go into this direction. So in order to show how this works, I actually chose a scientist at who is working at your university. Dia suggested to choose Masahito Hayashi. I hope I pronounced the name correct. So I chose him as an example scientist to give some personalized some personalized suggestions. So what I've done is I use all of his papers from the last 15 years, which are roughly 190, and I put them into, I analyzed the concept that he is using. So he's using roughly 300 individual concepts from this 6,000 total concepts. In comparison to me, all of my papers, I use roughly 100 different concepts. So this is significantly higher. So now I want to identify research interest or research concepts that Masahito investigates significantly more often than the usual quantum physicist. For that, we can calculate the probability that Masahito uses a specific concept compared to the probability that the general quantum scientist uses that concept. And this gives us, the ratio gives us a R value. And I sort now is 300 concepts by this R value. And these are the top 20 concepts that Masahito is using. Number one is the quantum Steinslammer. And I've only learned yesterday that this exists, but apparently my semantic network knew about it for quite some time. So that is the top research interest compared to other quantum scientists from Masahito. Other concepts are quantum Shannon theory or Holebo capacity, and so on. So this could be considered the research interest of the scientist. And I thought, if we have now one example, why not having two examples? So I took a second person, which is the host, and I analyzed all of the papers of Kishore. So I put them into a file and analyzed the concept that he is using. And again, ranked them by this R value, by the significance of that he puts in it, or the research interest that he has compared to the quantum, to the general quantum scientist. And here we also see those seem to make a lot of sense. For instance, machine learning, obviously, quantum foundation, obviously you wrote this review about machine learning quantum foundation, so it is perfect. Quantum contextuality, so it seems this ranking is okay. reflects in some way your research interest. I'm curious what you say about this. Maybe you can.
Yeah,
say.
I agree. I mean,
Sorry?
I agree. It's a very nice way to probe like what a person has been thinking all along. I mean, yeah, I mean, I mean, is it available as a like some kind of app for you? Like, I mean, I would like, for example,
Yeah, you should make it open source. No?
yeah, I mean, so that like suppose I want to,
It
let's say,
confirms the has hypothesis.
Sorry?
No, it confirms the has hypothesis about Kishore.
Yeah, yeah.
That's true. That's true.
Yeah, so I have
So
I have
Tiha has the theory that Kishore is not a physicist.
so yes, perfect. I also choose Tiha because he just graduated and he's my colleague and said he will join. So I thought this is also fun to also choose Tiha. So the tool is on GitHub, but I don't have the full semantic network on, and I can kind of also not publish the full data because I had to sign that I don't give it from APS. I could definitely do it with the semantic network itself, which doesn't contain all the data, but I didn't do it yet. I didn't write it in a nice enough way. So this was just me yesterday copying a lot of papers from archive from all of you three. Yeah, and analyzing.
this is amazing, Mario. Like, I mean, this is just
Thank you,
amazing.
thank you.
Yeah.
Okay, so this is only the first step. So now we have your research interest. Now, what I would like is the suggestions. So I was thinking it makes sense to have suggestions between your research interest and all concepts that exists, at least in this semantic network. So with this 6,000. And then, for instance, you could look which of those things are not connected, but are very highly predicted. And this is the second thing that I've done. So here, I took your personal research interest, and in the first column, or this first part, predicted, are the highest predicted concept pairs that are not connected yet, or at least not 1.5 years ago when the last update of my database I did, and which are not connected, but which is highly predicted to be connected in 5 years. So, and here for Masahito, one of the highest predicted one is actually something that when I saw it, I would find quite interesting. What is the connection between something like quantum metrology, which would be standard quantum limit, and hidden variable theory? I've never thought about that and how one would connect it, but just looking at it, I would probably spend some time thinking about it, what it could even mean. Now, you could also do something else. You could look at concepts that have very different semantic meaning, and you can look at this in the semantic network itself by analyzing a value that is called cosine similarity, which gives you the number or the ratio of shared neighbors. If the shared neighbors are very similar, the concepts are very close. If they are very different, also the semantic meaning is very different. And here in this second triple, I plotted the highest predicted ones that are quite unorthodox. That means that have very small overlap, semantic overlap. And for Kishore, I find this first one quite interesting. So there's a lot of geometric ideas in this contextuality and non-locality study, but the network predicted that pre-geometry, which I didn't know before, I also only looked it up yesterday, that pre-geometry would be something interesting to study, and it predicted it quite high. Also for DIA, there are some quite interesting things. For instance, this photon counting, how much entropy does counting of a single photon produce? Never thought about it before. I saw this, and that question came into my mind just because of this highly predicted but unconnected thing. Okay, so there's obviously a lot to do. That is a very first step into this goal of having maybe some inspiration of new ideas in the future. So some additional things one can do. So one of my goals would be to have a tool that can give you personalized, surprising, and fruitful suggestions for the future. Personalized, we have seen in the previous slide. We can kind of look into the research interest of the scientist, rank it, and it gives maybe reasonable ranking of the concept. Surprising, you could think about either network theoretical tools, like you tune the cosine similarity or the decreed centralities and so on, or you could also think about what are outliers in the semantic network in some network theoretical sense. So you could apply anomaly detection in this semantic network. For instance, you can easily think about it in a three-dimensional space where you plot on X, you plot the prediction from the neural network, Y, you plot the decreed centrality, and Z, you plot the cosine similarity. You get a space. And what are the furthest apart concept pairs that appear there? They seem to have some exceptional point in the semantic network. And now last, and this is very difficult, but probably could be very important, I think, would be how to get fruitful suggestions. So for that, one could augment the semantic network with some proxies of success. So a proxy of success, the simplest one, could be number of citations. But computational sociologists study many other proxies of success. So the idea would be not only to predict what will be connected, but also predict if it is connected, how impactful would it be? How many citations in the simplest case, or how important would this connection be? And that would be really useful then when you have a tool that can give you new concept pairs or concept pairs that are never studied together, where the network predicts that it would be quite impactful. So that would be very interesting. And I would like to close with two questions where I'm really interested in your thoughts. The first question: how does a human define new research projects? Is it in some way, in some abstract way, similar to what I've shown here, or is it completely different? And the second thing is, let's say you have now a tool that can suggest really good ideas or help you to think about new ideas in a very successful way. How could you actually evaluate such a tool? How could you say, yeah, that tool is actually quite good? How could you evaluate this? I'm very interested in your thoughts about it. Thanks.
Very nice talk, Mario. So, are there any questions from the audience? Like, please just unmute yourself and ask.
Mario, do you think machines will one day take over humans in formulating new concepts?
Sorry, can you say again?
You think
Mm-hmm.
if machines can ever take over humans in formulating new concepts, new ideas?
I think that they can. So what I definitely think is that they can help finding new ideas. How far this goes, I don't know. So your question can maybe be reformulated. Can a machine itself give you a complete new research idea that the human looks at and immediately understands and don't need to think itself anymore?
That's right.
well, I don't see how this would work at the moment. But I can
No,
also
not at the moment.
Yeah,
But
I can
maybe
also not,
100 years from now,
I cannot
1,000,
exclude
or even 500 years from now.
I cannot exclude this. There seems to be nothing that is kind of missing. Imagine if the semantic network has more than just pair correlation, if it really has some if from the paper it really gets more context than just it is connected together, but maybe also in what sense, and maybe not only pairs but triplets or larger ones. If it then finds some outliers or some things that seem to contradict, it can point this out and just say, hey, this contradict each other, look into this. And then that would be a very simple one, but I could imagine this is possible, and not in 100 years, but soon. What do you think?
Yeah, I've always thought that some of these so-called ideas that humans formulate could have been put together logically to a machine. If
Yes.
the machine is configured the right way.
Yes.
Maybe not in the next 100 years, maybe in the next 300 years. So I'm trying to think of how we as humans think of science at the moment compared to Isaac Newton.
Yes.
I think there's a lot of improvement in our way, the way we formulate connections.
I mean,
we're also not just,
sorry.
We're gone very much into specific, and yet we are able to connect across the boundary.
Connect to what?
Across boundaries like biology, physics.
Yeah.
Although we are working primarily in physics.
So I would, with this tool, one of my main motivation is to actually find later to increase it, not on quantum physics, but physics, maybe add chemistry, maybe add mathematics and computer science, and then have a very big semantic network, which can see science in a much bigger way.
Yes.
So probably what you very closely, I think how I understood what you just said. Yeah.
Yes. Yes.
Yeah, that would be great. Because humans, because of this, because of the growth rate of papers, humans cannot do this. They cannot keep track basically of their own field. Quantum physics already 800 papers per month. I mean, it's crazy. You cannot even read the abstracts of them probably. So
right.
Yeah.
Hey, Mario, can you hear me?
Yes.
Hey,
let me just. Yeah, sorry. So I was just wondering about basically data management. So you have basically n of these nodes, right? And you're trying to, in principle, draw a line between every pair. Then there is n.
Yes.
And let's agree that perhaps not all of them are meaningful. Perhaps a vast majority of them are meaningless. In the sense that they give you like Marxist for non-counting, or just meaningless phrases that you can string together. For various kinds of. Now, how do you, so my worry is following that basically you just have a large data problem on your hand, in the sense that the network, as the number of nodes n keeps increasing, that the number of basically suggestions that the computer can put up to you as potentially reasonable suggestions also keep going up. But if we agree that basically scientific pursuit is a little bit like trying to find a needle in a haystack, then it's not. It's going to be that a large variety of those suggestions are perhaps not particularly. So, is there a kind of filtering process where you have a very, very selective set of ideas that come out every time?
So here I didn't apply, for the examples that I gave, here I didn't apply any filtering. I took the, from Masahito, the 300 vertices combined with the 6,000 that exist in the whole one, which is 300 times 6,000, which is 6, 12, 18, yeah, a large number. And then I didn't apply any additional filtering. So what comes out here looks actually quite reasonable. So that is also in some way surprising to me that they look at least in some way reasonable. Even if you have now thousands or millions of possibilities, that it kind of can extract those that seem reasonable. Even if there's not, so at that point, there's not a single paper that combined universality and vital semi-metal. But I could imagine that somebody thinks about this or can come up. So I'm also kind of surprised that, yeah, something that it looks kind of reasonable. And that's why I'm motivated that such approach could work, if already the simple techniques work in some way.
Yeah.
Yes, the other comment I just wanted to make very quickly was that, I just wanted to know your reaction to it. It looks a lot like this is very good at starting new fields, but let's say, Adan was speaking a couple of days ago, if you just ask what's the next big problem in contextuality, right? I mean, that's going to be a completely, you have to go through the literature in a completely different way for you to kind of be able to predict what that object is. So could you speak to that, like in the sense that instead of trying to give a bird's eye view of all of science or all of physics, could I take the opposite approach, which is to say, let's say, take all the quantum machine learning literature that's sitting around, put it through your machinery, and then let's say predict what we should be working on in the next year?
So the things that it predicts, when you take the whole network hub, when you take the whole one, these are usually not the very surprising things, because they are predicted very high, and usually the things that are predicted high they're predictable, which is kind of the opposite of surprising. So prediction alone cannot give you something very surprising, I think. And that's why I was trying for quite some time. Actually, this was the most time that I spent with the semantic network trying to find some ways to extract actually some more surprising things. I was reading a lot of literature about surprisingness functions and so on. Unfortunate that never really, those things, you can probably not really formalize what surprising means. At least I was not able to do, but you can do some simple things like making the distance of those words larger. For instance, by reducing the number of shared neighbors. If they don't have many shared neighbors, they are conceptually quite different. And then highly predicted plus quite different could give something like what you would like to see. You said one needs to think very differently. So that would be very different, if not even the neighbors are connected. And yeah, but I don't have, this question is by far not even close to solved. I'm there somewhere epsilon square half, which is not very large.
Sure, no, I think, yeah, this is a very interesting direction to think. Thank you very much.
Okay, there is a question from, I think, Jose Ignacio has some questions. So
yeah, hi, Mario. Well, I wanted to share with you something I did on semantics and physics.
Cool.
Yeah, although I never published this thing. So the idea there was we took the abstracts of all the papers of every scientist. We produced a corpus of concepts as similar as the one you have done, less professional, let me say. And that attached to a scientist would define his vocabulary. So I am very similar to what you are doing here, okay?
Oh, that's pretty cool.
Okay.
How did you come up with the concept list?
We simply did we scanned the abstracts, and we took out the stop words. We took stemming.
Okay.
We did a standard analysis. Okay.
So also
what
kind
happened?
of like rake. Yes. Okay, I see.
So what happened is that finally we had every scientist define as its vocabulary. Okay. You are what you talk about.
Yes.
And then we could define the frequency of use of these words. So on top of the list, the frequency, so the relevance.
So
And then you could define the probability of use of these words in his papers. And that defines the probability distribution. So every scientist was a probability distribution. And then you can define distances. You can define whatever, distance you want.
Yes. Okay.
And you can really cluster them. Okay.
Mm-hmm.
And what we did is that we would tell you whether you would be a boring scientist, in the sense that you are doing the same as the average. Okay, you could define the average scientist.
Yes.
So therefore, you are a commodity, and you can be forgotten by the community, or you are in some sense original. Then we could invite you to know a colleague that would work on similar things, and more interestingly, to meet the colleague which is distinct and different from you, yet they bring something. I think that Alba was in the set of people, if I remember well. That was in a conference.
Yes, it was in Menasque.
It was in Menasque, yeah.
Yes.
And we offer everybody the map of relations. That, may I say, was not infinitely. We were recommending everybody to meet 3 people which were complementary rather than the same as they were.
Okay.
And that was okay, but what was, so you see, the focus is, in your case, is concepts. In our case, was people. So
yes. But
is science
you go one step
by concepts or by people? No, that was the difference.
Yeah, yeah. But then you define them via those lists. So you go one step further from such a list, or you combine this list into one probability distribution. Or?
That's it.
Yeah, that's pretty cool.
Yeah. Mm-hmm. Because you see here, you don't know whether the guy did a single mention out of politeness for local distinguishability, or he's, very heavily working on that. So that's the difference. And but let me just tell the funny piece, which is that we did the same thing in a workshop that was related to people working in innovation, simply in innovation, not in physics. So business people. And the idea that almost everybody was using the very same words in innovation. Okay, and that you are a commodity, and therefore if you are fired, you cannot find a job because there is nothing special in you. That was really spectacular. How it impacted much more the people in innovation than the people in science. Okay, because you suddenly realize that you are really nothing special. Okay, you are not originality. Yet, what we use, the tails of the distribution are the non-obvious words. So you have somebody had China, and some other had whatever. Okay, that was not with the LinkedIn's. And what happened is that there we propose that people that work in different things, but they have some strange, peculiar word share, they meet. So both were having some dealing with China. And then here you come, you're in a different country, and suddenly you meet another guy who is doing crazy things as you. So this idea of connecting people through the more sporadic words, which are really, it's very appealing. And I think in science, it would be great. So the most exceptional words, meeting a guy who knows finally, I know about the Dick model. I know it would be in my list somewhere. So now I know I can talk to Masahito about the Dick model or yeah, because this is surprising. So I think that exploring the quantifying the dictionaries or the probabilities is a good thing. And second, looking for non-obvious connections rather than the obvious connections. So discard the obvious Okay, everybody follows the fashion. Okay, discard that, because I think that discovery is more attached to opening something which is not well understood, words which are non-obvious, and then you go into those directions. So I think that, as I said, discovery is related to exceptional relations rather than the commonalities in the sample. But it was a lot of fun, amazing. And we had a wonderful present web page that you again had these plots that they move and you can put them apart.
Do you still have them?
Yeah, we have them. Yeah, I can pass that to you. Yeah.
Yes, definitely do this.
Yeah, yeah.
Cool,
I will
cool.
pass it to you.
I'm also thinking how to, so what you just said, this exceptional links, how this would be, what this would mean here. I need to think about it, but it's definitely a very good comment. Well, I mean, it's a very cool story. I was not aware of it. Definitely cool application also in the innovation field. But also what I can learn of your story for this project. That's interesting. And definitely think about it. Thanks. And
Yeah,
please
let me
have.
tell you that on a different basis, we are doing now a classification of human texts written. Okay, and we are doing something similar. We do every document is a dictionary because the words are used with a given frequency, and when you and therefore you can build a complete list of how the words were voting to a classification in a document. You collect this data, you have a final matrix, and now when a new document comes, word by word, they vote to categories. So you have a voting system, and it works extremely well. We get very high levels of classification of of text.
You classify the content, so you can say these two papers are quite similar. So
that's it. You are classifying. We are making a classification into 65 categories. So that's. But this idea that what you are doing through that thing is you are seeing the correlations that were hidden in those texts. This is what we're doing through a voting system, from all these correlations, anything. And the nice thing is that we are mapping all these probability distributions to the cats, to a cat.
What?
So actually a single state contains all the information of the document in the sense of correlations. And you can apply, now quantum classifiers to these things, where you have encoded the classical information as the probabilities of the words. So you use the semantic analysis as the encoding of that document into quantum state. Okay.
Okay. So, and this is where quantum machine learning goes in.
Yeah, which is fun. And we have very good classification rates. Very good.
What are the 60 categories? Are they scientific?
Well, in this particular case, it's for a bank, and they have 300,000 documents classified in 60 something categories, and they want to talk that. Okay. So how do you do that? Well, you have to do a semantic analysis.
So these are not scientific documents. These are
no.
Okay, I see.
Yeah.
Okay.
Anyway, I just wanted to tell you the story of the scientist.
Please.
How disappointing is to discover you are nobody and that you're doing the same things as everybody else.
Yeah, that would.
You are not Einstein. And
yeah, I mean, if you are exactly in the center, this would be the most disappointing thing. So you are in the most.
Exactly sounds like me.
Yeah, nobody.
Yeah. When outside is okay, you can say at least you do something different. No one cares, but you do something different. But inside, that would be not good.
No, I think if you
have something, please forward it. I'm really curious, especially how you go from here to get this distribution for scientists, and also would like to try it myself. A bit scared actually. I don't know whether I want to do it.
Cool. I think there is a question from Amol. So like he has raised hand. So like, Amol, can you like,
Yeah. Can you guys hear me?
Yes.
Oh yeah. So Mario, really wonderful talk. It was really nice. The thing that I'm thinking of is like along the next steps for this. Like I know using text is really easy, but particularly for physics, it seems like equations probably play like a really huge role, right?
Yes.
And I know it's very difficult to take the equations out of the paper, but have you like thought along those lines?
I, uh, so I definitely agree that equations are extremely important. So I thought about just that it's important, but I have no idea how it would extract. I know that there are, so a document is text, pictures, tables, equations. I know that there are tools from a few years back that can extract information from tables and surprisingly even pictures. But I don't know whether something like this exists for equations. And I definitely don't want to start this myself. So if that would exist, but kind of it should exist, right? That sounds like something very important. If people worked on this for pictures, so yeah, so I definitely agree. That's very important. But this goes then much further. This would not be only the abstract, but that would be you want to extract much more information from the paper itself.
Actually, I was going to ask you the same question.
Okay.
But in fact, it will go one step further if you have P implies Q type of statements. If you can do that, then one can actually push the frontier a lot more.
You mean when that would mean when your connections are not only co-appearance connection, but actually really
Logical.
relations.
Yes, logical.
So I thought about this the first time in 2015. So this is a super long-term project that I always worked on the side, and most of the time I didn't know how to continue. And also nearly I gave up on this and not publish, but then I said, okay, I write this text down just for myself in 50 years. And the first thing I thought about was also these relations that you see this corresponds to this in that specific way. And that was where I was extremely struggling. How can you even start anything like this? Because I don't want to do this by hand. And I had no idea how to get to such a relational or very sophisticated semantic network. So at that point, a few months after that, I found this paper, which seemed to be a very first step. I still don't know how to make this second step. It would start with something much simpler than what you suggested, just getting from a sentence the relations of two phrases or something like this. And people work on this. But what you say is then the final, the final thing. Then you have, or can have the complete information of physics, of written physics by human scientists in a semantic network and can do derivation. That would be absolutely fantastic. Then, yeah.
Mario, like, I have a question. So
Sure.
I mean, recently I had the chance to read about Bayesian networks and like causal models and so there's this book Book of Why, and I think in one of the email conversations with you I mentioned that.
Yes. Right.
So Julia Pearl, who is a proponent of this Bayesian network and all, and he says that I mean there are three levels of
understanding.
The first level is this association, where we try to find which variables are related. The second level is about intervention, I mean the way child does something, like intervenes and then see what happens. And the third level is the counterfactual reasoning, like the way Einstein would think, if I go to let's say I start traveling at speed of light, what will happen, and so on. Most of the I mean almost all of the machine learning that we are doing at the moment, that is basically curve fitting, just related.
Yes.
I mean that's I mean that's the criticism of Julia Pearl to current AI, current AI.
Yes.
And he says that if you want,
agree.
and if And I said that if we want to, but it's amazing that, we can do so much things just by curve fitting. But, and maybe it could be possible that at the end of the day, everything is curve fitting. I mean, okay, it's all like, yeah. But then he says that, if we want to have like the true AI, I mean, which can reason and do counterfactual reasoning and all, then we need to, like develop all this kind of do why kind of, like we need to, I mean, the machine need to ask the question why, like, I mean, why the machine did it, and let's say if the situation were different, then how would it would have responded, and like I mean, the way like from scientists like think about, like counterfactually. So what is your take about that? Like, I mean, with using Bayesian network and all, like have you thought about, like, instead of like correlations, can one think about, some kind of causal diagram and say that this concept led birth to this concept, and then like how the like, for example, we can think that, like information theory and quantum mechanics together led to quantum information, and then like the causal structure, like, I mean,
yes, led to the qubit. Yes. So the very first thing before I started this, I thought about, if you really want to do automated science, you would need this concept, and you would need derivations in this whole sophisticated semantic network or reasoning in there. That at this point I didn't know how to continue in that direction. So in some way, what I'm trying to do with this, and also with some other projects, is not solving science with AI, but having AI that can inspire scientists for things that they would not think about themselves. So that is definitely a step lower, but that is a step that we can do right now, and that could have real impact. So I would find it extremely interesting if somebody comes up with first the data, which would be probably this huge semantic network with all the clever relations and so on, and then be able to reason in there and so on. But I don't know how to get there.
Yeah, I mean, something like, like take a list of concepts and then like do some kind of Bayesian network structure learning by like running over archive and like, I mean, say, like taking the archive data and like so on. And I'm just, I mean, I haven't thought about it, but like, just,
yeah. So how,
yeah.
How would you build up the data? How would you build up this semantic, this relational network, which you need as a start?
Yeah, so I'm thinking something Bayesian network structure learning. Like, I mean, like I would like to have the directed acyclic graph structure, right? To like know that how does the causal information is flowing and all. So I will take a set of like, like similar to your case, I will take a set of nodes, and then I would like to know the directionality. So for that, I will, like, I mean, the trivial thing which I will start with the Bayesian network structure learning, and try to by using the information which is there out, try to find directional connections.
So can you give can you say concretely in maybe this example? So here there are three examples. For instance, let's take maybe the second one. Here it says we studied the quantum dynamics. So quantum dynamics could be a concept of a Michelson interferometer with Fabry-Perot cavity. Blah blah blah, and driven by a single photon and optomechanical. So how would you build up this knowledge network with such a sentence, with your Bayesian approach?
Yeah, I mean, it could be difficult here, because like, I mean, because you can take these nodes, these concepts as nodes, but then there may not be, like, I mean, this kind of like directed connection. Like there could be connection, but there may not be directed connection.
Yes.
Yeah.
Yes. So there was a book from a, I don't know whether I find it now, probably not. Ah, yes, wow, I found it.
Oh.
In this book, so this person has found 65 different relations between words where you can describe every English sentence. And he gives them in, he gives those relations in total formal way. And he says he can build up the entire knowledge of arbitrary grammatically correct English sentences with his model. So that could be something to start with. Do you see it now?
Yeah.
Okay, good. So here he has totally formalized every possible relation between English words, and he also builds up graphs of them. And he says there's a finite rule of how you can encode information in English sentences. These are 70 rules or something, or 70 relational structures. So one could start from here potentially, get all this relation, what you probably want. Yeah. Then I don't know how to continue. I mean, it sounds extremely challenging building this up, but then I would not know how to actually continue with reasoning and so on. But yeah, I didn't think too much about this further. So yeah.
What's the name of this book? Like
Knowledge representation and semantics of natural language. You can post it to the chat. But I don't know whether people followed up on this. This was something that I've seen before I started, because before I found this much simpler biochemistry paper. Yeah. So I don't know whether it's a good starting point, but yeah.
Thanks a lot. I mean, I definitely would like to have a look. So, are there any more questions from anyone in the audience? I mean, if you have a question, just unmute yourself and please ask. Yeah. So, Mario, it seems there are no more questions, and I mean, it was really, I would say, you made it a personalized talk, like, for the audience and all, and so thanks. Like, you really took effort and all, and the discussions were amazing. Like the question from the audience, I really liked it. So thanks a lot, and we would like to have you again at some point again in the journal club. I mean, in future, and
sure, if there's some progress. Thanks a lot. That was really a very fun talk to give. Talking in between and getting a lot of very good questions and also stories. That was really, really enjoyable.
Yeah, I mean, Jose's story was amazing. Yeah, and yeah, so
Mario, I think, has another talk on how to set up optical circuits. That would be interesting. Automate the whole setting up of the all the gates.
Quantum optics.
Yeah, quantum optics. Yeah. I find that very interesting.
Would be happy to also talk about this at some point.
Okay. Yeah, that would be great. Yeah.
You can talk that in our group meeting, like, I mean, which is separate from the like this machine learning journal.
Yeah. So because there are people here who are doing actually chip-based quantum optics, and I think an understanding of that would be very useful.
Yes, certainly. Would be happy.
Yeah, it would be good collaboration.
Yeah. So thanks a lot, Mario. Like, and this was really amazing, and yeah, like.
Thank you very much.
The people enjoyed a lot. So thanks for joining, and I think we can stop the recording now probably.
Yes. Yes. Thank you very much.
And thanks everyone for joining.